So in this video cast, we'll continue to look at how concentration changes with time, and make sure that you've got these equations in front of you for 0, first, and second order integrated rate laws, and then make sure that you've got the problem sheets in front of you, and we'll begin right here with the problem that says the decomposition of dimethyl ether at 510 degrees Celsius is a first order process with a rate constant of 6.8 times 10 to the negative fourth. Pause the video now if you need to get your your calculator, your pen or pencil, or this paper out so you can take notes. All right, it tells us this is a first order process, and it tells us that there's an initial pressure of 135 torr, and then it has a partial pressure that we don't know at 1420 seconds. Well, if you remember back from the very beginning of the chapter, we talked how pressures are proportional to the concentrations of substances. When we're talking about gaseous reactants and products, they're both proportional to one another. So we can simply replace in the first order integrated rate law equation pressure instead of concentration. And the equation for first order integrated rate law, if you remember, looks like this, where it's the natural log of concentration is equal to negative kT plus the natural log of A original. And instead of having concentrations here now, we'll have pressures. So our equation becomes natural log of pressure at a particular time is equal to negative kT plus the natural log of pressure original. I use a little O down here to mean original, okay? So we can set up this equation and say natural log of pressure at a given time is equal to the rate constant, which is 6.8 times 10 to the negative fourth per second, times the amount of time that it takes to get there, which is 1420 seconds. Make sure that you've got your units correct. Your seconds match with 1/seconds, plus the natural log of the original pressure, which is 135 torr. So 135 torr, natural log of that. So if you plug this into your calculator, this 6.8 times 10 to the negative fourth times 1420 plus the natural log of 135, you get the natural log of the pressure is equal to 3.939. And some people are confused about how to get just P here from natural log. Obviously, you can't divide both sides by natural log. So on your calculator, if you just want to take a look at mine, which is somewhat similar to yours, go ahead and find the button that says ln, and right up above it is this little e to the x right here. Let's see if I can zoom in on this a little bit. You can see e to the x. That's like the undoing of the natural log. And since it's in yellow up here, I have to hit the second key on my calculator. So I'll hit second, and then I'll hit the e to the x key, and that puts on the screen, it puts a e with a little caret. And then I'll type in the number 3.939, and then I'll hit enter, and I get 51.4 approximately if I round. So pressure 51.4 torr, that would be the partial pressure after 1420 seconds. So that's solving integrated rate law equation for a first order process. Second question, look at the graphs below. Look at the graphs below. What do the y-intercepts of graphs A and B represent? Well, first of all, take a look at the y-axes and see what they're labeled. Okay, and if you look here, this one's a little harder to read, but it says pressure of the chemical in torr, and this one is ln of the pressure. So remember, pressure is analogous to concentration, so the y-intercept is where it would start right up here, and this would be the original pressure of the chemical, or the starting pressure, or if you looked at it in terms of an equation, it would be the one with the subscript little o or little zero. Now, if you look at this one right here, this is the natural log of the pressure, so this would be the natural log of the original pressure. And And they're both kind of interesting graphs because if you look at it, this one's a curve when it's just concentration or pressure versus time, but this one gives you a nice straight line when it's the natural log of pressure versus time. And if you remember, looking back here from our graphical information when we made this table about integrated rate laws, what type of graph gives us a straight line with a negative slope where natural log of concentration versus time gives us that straight line? If you look up here, well, that is a first order type reaction. So just by looking at these graphs and knowing that this is the natural log data of this, you can say that this must be a first order process, because the only way to get a straight line is by graphing the natural log versus concentration. Not part of the question, but an interesting concept to go along with it. Let's go to the next page. Here we're given a bunch of data, and it says the following data were collected for the gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. And then they give us the balanced chemical equation and some time versus concentration, or concentration versus time data. Is the reaction zero, first, or second order? Well, one way we can find this out, and probably the easiest, is to take and graph concentration versus time, and then we could graph the natural log of concentration versus time of this same data, and then we could graph 1 over concentration versus time. And whichever one ended up giving us a straight line would be a clue as to whether it's zero, first, or second order. And of course, if concentration versus time gives us a straight line, we'd know it'd be 0th order. If it's natural order, concentration versus time would be first order. And if it's 1 over concentration versus time, we'd say it'd be second order. Well, lucky for us, look at this. Here are some graphs right here to help us with the answer. And if you take a look at the caption for these graphs, or just the units, you can see that this is natural log of concentration versus time. And notice it's got a little bit of a curve to it. And here's 1 over concentration versus time. And notice the nice, sharp, straight line that makes. So looking back at these, remember 0th order would be a straight line with a negative slope. Natural log of concentration versus time would be a straight line with a negative slope. And second order would be a nice positive slope straight line. And that's the type that we do end up having here. If we took 1 over every one of these concentrations and graphed it right here versus time, we'd get a really nice straight line. Now, it's not very often that you get a question like this, but they might give you different samples of data or give you different graphs of the data and ask you what kind it is. So you need to memorize, and just flat out memorize that 1 over concentration versus time is second order. Natural log versus concentration versus time is first order if it gives you a straight line. So this must be a second order reaction. That's the answer right here, because the straight line with a positive slope indicates that it's going to be a second order type reaction. Second order. Last question on the page says, consider again the decomposition of NO2 discussed above. The reaction is second order with NO2. We just figured that out. With a K right here of 0.543 per molarity per second. If the initial concentration of NO2 in a closed vessel is 0.05 molar, what is the concentration, or the remaining concentration after half an hour? 0.5 of an hour. So the second order integrated rate law equation, if you forgot what it was, is right here. 1 over concentration is equal to K to positive KT plus 1 over concentration original. So 1 over NO2 would be equal to K, which is 0.543 molarity negative 1 seconds negative 1. Remember, that's positive now, times the time. And be careful, because what are the units here for the rate constant? Per second. And what do they give you the time in? Ooh, hours aren't going to match seconds, so you're going to have to do some conversion here. And there are 3,600 seconds in an hour, so half of that would be in a half an hour. So that's 1,800 seconds that you have to put in there. and then 1 over the original concentration, which is 0.05 molar, so 0.05 molar goes in here. Multiplying these guys together, we end up with 1 over NO2 concentration is equal to, multiplying those together and then adding 1 over 0.05 gives you 997.4, and then taking the inverse of this, or the 1 over of this on your calculator, you get the concentration of NO2 equaling approximately 1 times 10 to the negative third molar. So you can see the concentration dives down after about a half an hour or so. Okay, Next page has a really nice graph on it, and you've seen this graph before. You used this graph before to show you where to find the initial rate to start with by finding the slope of the line tangent to the curve. And they ask a new question about it. They say the reaction of C4H9Cl with water is a first order reaction. The figure above shows how the concentration of this changes with time at a particular temperature. From the graph, estimate the half-life for this reaction. So the half-life is, remember, when half of the substance is remaining. And if you look right here, we start with 0.1 molar concentration of it. So if we're going to half of it, we'd go to 0.05. Follow that over to the line, which is approximately right here. Drop it down, and in theory, this should tell us the time if I can draw somewhat of a straight line. It looks like the half-life is between 300 and 400, maybe a little closer to 300. So for letter A, maybe 325 seconds or so. That's about the half-life that we can estimate graphically. Okay, and then it says in letter B, use the half-life from A to calculate the rate constant. And if this is a first-order reaction process, which they say, remember the half-life equation is independent of the amount of concentration that you start with. T1 half is equal to 0.693, or the natural log of 2 divided by K. So natural log of 2 divided by K is equal to T1 half. And we know that the half-life is equal to 325 seconds. And this is equal to 0.693 divided by K. So I'll multiply both sides of the equation by K and divide both sides by 325. 325's cancel, K's cancel, and I get T1 half equal to, let's see, 0.693 divided by 325, and I get a K equal to, I put T1 half there, I put T1 half in there, a K equal to 0.00213, or 2.13 times 10 to the 123 negative third. The units on that guy now, it's time right here in seconds, so I'd end up with 1 over seconds, or seconds to the negative 1 for the K or rate constant for that reaction. Last page for this section. Let's see, calculate the half-life for the decomposition of an insecticide described in the sample exercise above. I believe that was in the video cast before. It told us there that the insecticide follows first-order kinetics with a rate constant of this many years, 12 degrees Celsius, and the tell us an original quantity. But since it's a first-order kinetics, remember it follows the first-order kinetics half-life equation then right here, which is T1 half is equal to 0.693 divided by K. So T1 half is equal to 0.693 divided by K. It's independent of the amount we started with, so we really don't need to know that concentration at all. It's extra information. 0.693 divided by the K, which is 1.445 year to the negative 1, so our units should come out to be in years. And we should end up with 0.4795 years, which means it takes almost half a year for it to go down to half the amount of concentration. Second question, how long does it take for the concentration in the insecticide to reach 1/4 of the initial value? Well, this is how long it took to get to half the original value. How long would it take to get another half? In other words, to get another quarter. Well, it took approximately half a year to get to, and this is pretty approximate because it's 0.479, but it would take another half-life to get to a quarter, because if you're looking at it, if we start with an amount of 1 and we work to half and then we get to a quarter, which is 1/4 right here, the first time it took 0.479 of a year. Well, now it would take, and if I round that to half, it would take almost 1 year for that to happen. Now, technically, I guess if you did math, it would be 0.95 or something like that of a year. But you can see that half-lives are kind of regular. You know, you go from 1 to half to a quarter to an eighth, and you know, it'd take another half-life for that to happen, to a 16th, etc. How does the half-life of a second-order reaction change as the reaction proceeds? Well, if you take a look at second-order half-life right here, you can see that T1/2 is equal to 1/K times A original. T1/2 is equal to 1/K times A original. And you can see that this half-life for second-order reaction is inversely proportional to the original amount. So if something follows second-order kinetics, it's inversely proportional to the original amount of substance or original concentration. So if they had a lot right here, then you'd have a very small half-life. If you had very little here, you'd have a pretty long half-life. So you can say that if you had a lot to start with, half-life would be pretty short. If you had a little bit to start with, the half-life would be pretty long. And so as the reaction proceeds, the dependence on the amount of original concentration continues. So lots, short half-life, little, long half-life. I think that's what they're getting at. Good luck with your integrated rate law equations and your half-life equations. Make sure that you take a look at this table and you're very familiar with 0, 1st, 2nd, particularly 1st and 2nd order data. You memorize the graphic representations and what they mean, where you find the slope and what the slope is. It's the rate constant, by the way. And what versus what gives you a straight line, and what are going to be your units for the rate constant down here.